So good morning, everyone. Good morning to the guys in the computer lab in mechanical engineering at Stellenbosch, where I am, and good morning to all the rest of you, wherever you are, yeah, at one of the many venues of the conference. So today we do something like an experiment, yeah, because you spent a week learning Linux and Python, and in the rest of the week you will keep learning about how to use Python to solve various numerical problems, from differential equations to machine learning to stochastic processes and random and Monte Carlo methods and things like that. But there is also another thing that Python can do, which is symbolic manipulation of mathematical expressions. Yeah, if you want, it's a little bit of an open source version of Mathematica. Yeah, and Mathematica is quite an expensive software package. Some universities have a campus license, but it is sometimes very useful to be able to do everything within the same environment, yeah, and you can use it at home and wherever you are, yeah. So the aim of today's two lectures and two tutorials is to give you a very basic introduction to SymPy, yeah. And you will see once you have the basic, it's fairly straightforward to put it in place to solve the problems that you might have. Yeah. So let me share this screen. Let me see if I can do that. Sorry, now here there's too much going on. Is it this one? Yeah. Okay. So voila. Sorry, I was just told by, sorry, 1 second. I did a mistake. I need to start from the top. You saw that we uploaded a few Jupyter notebooks, yeah, and Benjamin told me that that you're not familiar with it, but it's not a train smash. You can just cut and paste whatever you want in whatever environment you want to use. Yeah, the reason I chose to use that is that you see here at the top there's a little slide projection button, yeah, and if you print that, it looks like a slide. yeah, and it makes it probably a little bit easier to read. Yeah. So what I want to do this morning is a very quick introduction to the basics of this software package, SymPy. Yeah, and just to mention a few things. Yeah, the best source of information is of course the SymPy website. Yeah, so if you go to sympy.org, there are tutorials. There is the full documentation, which is I think 1,000 pages long. And it's just the tool where you go and search what you need. Yeah, I don't think many people read the documentation from page 1 to page 1,000, but when you know what you're looking for, it's easy to find. Yeah, and if you're interested in a more recent, of a couple of years ago, more academic paper on SymPy, I attach here the link. Sorry, I copied the link to the supplemental information, but it's the same link for the article proper. Sorry, that was a mistake. Okay, so what we will do is we will really start basic and use a very hands-on approach. Yeah? So I would really encourage you. I see from here already that some of the screen have already the Jupyter notebook open. We will go slowly, and you can just cut and paste and use it in whatever system you're using. Yeah. So, as all Python programs, you need to start importing a few libraries before using the importing SymPy. It might be useful to import NumPy and things like that. Sorry, these import warnings you can probably ignore. I had a problem yesterday, and that was the only way of getting rid of it. So don't worry about that. Yeah, but here comes the okay. This was just check what system version we are using. Yeah, which is not so relevant maybe. And here comes the important two lines. Yeah, so import SymPy. I import it as SP, yeah. Some people import it as sim, but you can import it as whatever you want. I think SP is nice because it's a little bit like NumPy as NP. Yeah, and then there is a nice, once you have imported SymPy, a nice printing command that makes all the equations that you use look fancy. Yeah. So if you type that SP init printing, you will see all the equations will look very nice, like printed in a book. Yeah. So these are the preliminaries. Yeah. Okay. So what makes SymPy different? Yeah. And just to to start really really elementary, yeah, let's give a look at numbers. You know that in Python you have integer and floats and so on and so forth. And for instance, if you do import math and you print the square root of 3, you get 1.73 blah blah blah. Yeah, you can do the same in SymPy. Yeah, if you add sp.sqrt of 3, it will give you square root of 3. Yeah, so that's the basic difference of SymPy. SymPy is essentially like calculating by hand. Yeah, if you look at if you need to calculate with square root of 2, you wouldn't always write 1.73 blah 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 blah. Yeah, it's very nice to have square root of 3. And now you see because you see the very nice square root of 3 like in a book. That's because of our printing command that we added at the top. Yeah. Is everybody, can I, it's easier for me to look at your faces than at the Slack channel. Is it okay that we proceed at this speed? Is it okay? Yeah. If there is any, just shout. Yeah. Okay. So. And of course, if you and now you see another nice advantage. If you do the square root of 8, yeah, it's 2 times square root of 2. Yeah, it's not some other fancy number. Yeah, float number. Yeah. Same goes by division by integer. Yeah. If you do it in straight Python, you do 1 divided by 7. Yeah. Even if you do one integer divided by 7, your result will be 1.2428 blah blah blah. Yeah. If you do it in SymPy, yeah, and you use this command simplify, yeah, the result will be 1/7. Yeah, just the fraction. Yeah, the rational number 1/7. Yeah. So simplify of an expression allows you really to write it as it is. Yes, you want 1/17, it calculates with 1/17. Yeah, it uses the rational number 1/17. Yeah, and you can get exactly the same result if you do it in this way. Yeah, if you use sp.rational, yeah, 1,7, it gives you 1/7. Yeah, and it works, of course, for every number. Yeah, this is just in the sense you can use it. You can use SymPy as a calculator in fractions. Yeah, without going to real numbers. Yeah, you can stay rational if you want. Yeah. Okay. Of course, SymPy has also the usual mathematical constants. Yeah, so you don't need to, if you want to use pi, yeah, 3.14 blah blah blah, you use sp.pi. Yeah, if you want to use the exponential, the e number, yeah, it's sp.capital E. Yeah, it even has infinity. Yeah, if you use sp.oo, yeah, that stands for infinity. Yeah, so if you do 1 divided infinity, it will give you a nice 0. Yeah. And it has also complex numbers. It has also imaginary numbers. Just square root of -1 is just I, capital I. So E is capital E and I is capital I. Yeah. And later on, I think in the tutorials, we will fiddle around a little bit with complex numbers and see how that works. Yeah. So that is really very nice. So when you do, for instance, later apply to trigonometry, yeah, you can just use pi as pi. Yeah, you don't need to get back to the numerics. And that's the beauty of the symbolism. Yeah. Of course, you can do also floating point operation if you want to, yeah. So for instance, let's go back to our square root of 2, yeah. If you now add the evaluation function, eval f, yeah, up to 5 digits after the comma, yeah, it gives you 1.4, what is it, 1.4142, yeah. If you add here, let's see if it will work. I don't know. If you put here 10, of course, it gives you 10 up to 10 digits. Yeah, so you can, if at the end of your result, where you have P's, I's, E's, and so on, you want the numeric number. Yeah, it's easy to calculate it, to evaluate it with eval f. Yeah, so you can always go back. Yeah. Now, let's see, how would you calculate, maybe without looking in the notebook? Yeah, I give you a minute. Try to calculate the first 100 digits of pi. Yeah, I give you just 30 seconds. Yeah, you have all the commands that you need. Or have you already done it? But you peaked. I can see from the eye that you peaked in the Jupyter notebook. Yeah, that's not fair. Yeah. Yeah, no, that's very easy. Yeah, so we can. So first of all, remember we need to call pi with sp pi. Yeah, and then you do the evaluation eval f. Yeah, the evaluation of the function, 200 digits. Yeah, and you see it's a little bit long, but you get it. Yeah, and if you want it to 200 digits, that works as well, of course. Yeah, I hope. Yeah, it's just oops, just a little bit longer. Yeah, but then, you know, if for whatever reason you need it, you can cut and paste it. Yeah. So this is very easy then. Yeah, and it works, of course, for every rational number, for every constant, and so on and so forth. Yeah, which also means that, you know, it's Python or SymPy completely replaces your mathematical formula collection. Yeah? If you forgot something, or your calculator, I forgot something, you can get it to whatever precision you want at any time. Yeah. Now, the sim in SymPy stands for symbols, of course. Yeah. So we need now to learn how do we force Python to operate with symbols instead of with numbers. Yeah. And that's what we do in this in this section. Yeah. So all variables in SymPy are defined as symbols. Yeah. And how do we do that? Yeah, very simple. For instance, if you have a mathematical expression that contains x and y, yeah, you need this command line. Xy is equal to sp, because we are importing SymPy as sp dot symbols, and then in inverted commas the names of your two variables. Yeah, in this case x and y. Yeah. So this is probably the most important lesson to learn. Yeah, because without this at the beginning of SymPy, nothing works. Yeah, so this is very useful. Yeah. And then, you know, you can, if you remember generic Python commands, if you want to check what is the type now of X, yeah, in the internal system of Python, yeah, it will tell you that is a SymPy core symbol in the class symbol. Yeah, just if you want to know the inner workings. Yeah, but that's not so relevant for us. Yeah. The nice thing is that, you know, in very often in mathematical expressions, be it physics, chemistry, medicine, maybe even economics, yeah, sometimes you need Greek letters, yeah, and you can do that as well, yeah. For instance, if you want to define your symbols as Greek letters, let's say alpha, beta, gamma, you just do SP symbols alpha, beta, gamma, yeah, and if you check, for instance, alpha, you see alpha is a very nice Greek alpha. Yeah, yeah, and you can check it for beta, for gamma, for whatever you want. Yeah, and it's even sorry, one thing that maybe I need to remind you. the notation of these Greek symbols is a little bit like in LaTeX. Yeah, who of you knows about LaTeX? Him. Okay, okay, one person. Okay, so and it's of course inspired by how you write it in English. Yeah, the Greek symbol alpha. Yeah, in LaTeX there would be a backslash in front of alpha, beta, and gamma. Yeah, but it's okay. So if you don't know LaTeX, let's not go down that route. Yeah. That's probably maybe something that we need to do in the next summer school, to do a little introduction to that as well. Yeah. Okay, so this is, so the symbols can also be Greek letters. Yeah, if you have to, that's, and you know, and if you forgot the English version of the Greek letter, just go on the SymPy documentation. There are tables with all the symbols and so on and so forth. That's really 3 seconds of Google. Yeah, but it's even more interesting than that. You know, sometimes symbols might have subscripts and superscripts. You can have that as well. Yeah, yeah. For instance, let's look at the symbol delta, a Greek delta with the subscript 1 and the superscript 2. Yeah, then it's easy. You do delta, the underscore stands for subscript, and the head stands for superscript. Yeah, and delta 1 2 gives you delta 1 2. Yeah, if you want, sorry, I don't have a slide for that. If you superscript say is 2 3, yeah, then you can put this in curly brackets. Yeah, you can put 2 3. Yeah, and why doesn't it work? Ah, sorry, I'm an idiot, because it will work here. Yeah, now you have delta. Ah, what did I do? Something went wrong. Okay, you see, that's the problem in improvising. Okay, let's kill it again. Sorry, I don't know what I did wrong here. Okay, maybe. Okay, this worked. Okay, sorry, something, you know, when you improvise, it's. But anyway, if you put it in curly brackets, you can have more symbols in them, in the exponent or in the superscript. Yeah. So in principle, the reason why I think that this is important is because you can really write the equation as you see them in the book, or as you see them on your piece of paper, yeah, or you see them on the screen in a lecture. Yeah, you can translate them one-to-one in SymPy, yeah, and start manipulating them. Yeah. So so far the important lesson was symbols. Yeah, you can use Greek letters, superscripts, and subscripts. Yeah. Now, what do we do with symbols? With symbols, we want to create mathematical expressions. Yeah, and the best way to do it. Let's see, for instance, we want 2 times x times y. Yeah, and of course, if I type an expression, yeah, it will be 2 times x plus y. Yeah, so this is 2 times x plus y in SymPy. Yeah. Now, once we have the expression, we can start manipulating them. Yeah, and that's where it becomes interesting. Yeah, because just to transcribe it, it's boring. Yeah, we can start manipulating them. Yeah, so for instance, the simplest thing would be to take our 2x plus y and divide by 2. Yeah, just to do something. Yeah, and you see, and it very nicely gives you x plus y half. I mean, we wouldn't have expected anything else. Yeah. So that works. So this is the basic strategy to do expression and to start to manipulate them. Yeah. But of course, x plus y is not particularly exciting. Yeah. Let's look maybe at a slightly more complicated example. Yeah. Let's look at this expression. Yeah. So we have e times sine x plus e times cos x. Yeah. And if we look at it nicely, you see the expression that we type. So this expression 2, yeah, is e to the power of x times sine of x plus e to the power of x times cos x. Yeah, and I didn't tell you how you get, but it's fairly natural how sine and cosine and all the mathematical functions are called in SymPy. Yeah, you just add SP in front of them. Yeah, as you would expect. Yeah. So this is very nice. Yeah. So And now comes the beauty. You see, if you look at this expression, it's fairly obvious that you could take the e to the power of x outside and in the bracket have sin x plus cos x. Yeah. And that, of course, SymPy can do for you. Yeah. So if you want to simplify, we could use the SymPy command factor. Yeah. And if we do that, if we do factor of the expression 2, it does exactly what I mentioned. Yeah, it takes one factor out, and in the brackets, it multiplies with the rest. Yeah, so you have e to the power of x times sine of x plus cos x. Yeah, so factor is a very important and useful command to remember. Yeah, because it allows you to factor expressions and make them look maybe a little bit more elegant and simple. Yeah. Maybe for some application, you have the factorized expression and you want it back in the original status, yeah? And then, of course, you expand it back, yeah? And what command will there be to expand it back? Expand, yeah? So if you do now, you see, factored, sorry, where was it? Factored was our factor expression, yeah? With expand, we expand it back, yeah? And, you know, in the manipulation of complex expression, one will sometimes one might be useful, sometimes the other might be useful. Yeah, so that's how it is. Yeah, okay, and this we can now maybe simplify even further. Yeah, for instance, you don't like the fact that there is the sine of x plus the cos of x. You would prefer to have just one of the two, yeah. And then, of course, SymPy knows all the trigonometric addition theorems, yeah. And if you now you force it to simplify even more, yeah, with the command simplify, yeah. Then you see it makes out of the sine x plus cos x the sine of x plus pi over 4, with the corresponding square root of 2 or whatever, yeah. Yeah, so it knows all the trigonometric function as well. Yeah, so that's really very nice. Yeah, so that you know, these are the commands that are very useful. Yeah, factor, simplify, expand, and collect. You can also use. It's a kind of factor. Yeah, you can force it to collect terms of the same type. Maybe you want to divide by something and you want to extract a certain term out of a bracket. Yeah. I didn't, sorry, I could have had an example for collect, but you know, maybe in the tutorials you can come up with an example for collect. Yeah. Okay. Now, I already used a few standard mathematical functions. Yeah, and but you know, if you go on the SymPy documentation, there are lots of them. Yeah. Generically, the strategy is, of course, you know, you just add SP in front of the name of the function. Yeah. For maybe the only ones that are really off the usual norm is the Arcus sine function, where you just summarize it with asyn. Yeah. And a cos and a tan and so on and so forth. All the other names are fairly straightforward. Yeah, you have the log x, you have the ln x, and you just remember to add the SP in front of it. Yeah. One thing that you know, can cause a little bit of problem is that if you Google around for SymPy code, yeah, pay attention, because not everybody imports SymPy as SP. Yeah, some people import SymPy as sym. Yeah. I tried yesterday to do a tutorial with ChatGPT, and promptly all the SymPy expression were sim dot something. Yeah, and you have to change it, or just tell him to import it as a SP. So even if you look in books, don't get surprised. I just you know, there is a freedom of what abbreviation to use to import things. Yeah. Yeah, so, and here is the list of all the SymPy functions. Now, if you go to the docs at sympy.org and you click around a little bit on the menu on the left-hand side, eventually you get to the list of all functions in SymPy. Yeah, it's you can try to do it if you want. Just click on that link. Yeah, no, you can't. If you are in the notebook, you can click on the link. If you are in Zoom, probably it doesn't work. Yeah. Okay, so that's fairly straightforward. Okay, now let's start maybe doing now a less trivial example. Yeah, you know, regardless of your discipline. Yeah, at some stage in your career, you've met a Gaussian distribution. Yeah, so let's try to do a Gaussian distribution in SymPy. Yeah. So now we need sorry, this I could have, okay, sorry, forget about the first line. You have it already because you imported the whole of SymPy SSP. Yeah. We need the symbols x, mu, sigma as symbols. Yeah, x, mu, and sigma. Yeah. And then here's our function f. Sorry, this is really pedagogically bad because now I don't have the sp dot. Anyway. And then f is the square root of 2 times p times sigma, the variance squared, times the exponential of x minus the average square over 2 times sigma squared. Yeah. And if you print f, then you get the nice expression. Yeah, you could force it to divide the square root of 2 and have the square root of 2 at the bottom if you want. You can use simplify or whatever, and that will work. Yeah. Okay, now, sorry, here's there's a typo. Yeah, so let's define now 2 Gaussian distributions. Yeah, and maybe I give you a few minutes to try. Yeah, and multiply them together. Yeah, and call the 2 multiply Gaussian distribution f mult. Yeah, f multiply. Yeah, and then you want to simplify it with SymPy and show that the product of 2 Gaussian distributions is again a Gaussian distribution. Yeah, can I give you a few minutes to try? So the starting point would be do what we did above for 2 Gaussian distributions. Yeah. I give you a few minutes and then so that I can have a sip of water. So essentially what I want you to do, sorry, no, I didn't, is to construct in SymPy with the relative symbols, the 2 distributions. Yeah. Maybe when one of you has it, just give a sign of life. It shouldn't take too long. I think there was Slack there, but it disappeared. Let me see if everybody on there. On Slack should be. Okay, perfect. What are we doing? Okay, Benjamin, please save us. Okay, sorry. I see there is the question. I can show you the here we have the yeah, the mu is just mu. Yeah, I see there is a question in the Slack channel how to do the Greek symbol. Yeah, the mu is just mu. Yeah, and then SymPy learns it. Yeah, and you see it really uses the mu1 symbol in the expression. Yeah. And for instance, if I were here to, let's say I want to see at F1, yeah, it uses it very nicely. Yeah. By default, it doesn't cancel the square root of 2 in the denominator, but we could force it with simplify if we wanted to. Yeah. So let's assume now do we all have F1 and F2? Okay, Kim has it. Yeah. Anybody else? Sorry? F1. Okay. Then let's wait another minute. So, but now cut and paste F1 and call it 2. Yeah, that shouldn't take too long. Yeah. Yeah, you need to change it. You need to just change the 1 and the 2. But the whole thing will have. Yeah. Okay. So now I'm assuming now you have both F1 and F2. Now we need to multiply them. Yeah. And if we multiply them, you see, the first step is, of course, it just has the two Gaussian distribution and it multiplies them. Yeah. Doesn't do much with them. Yeah. It just takes the two distribution and multiplies them. Yeah. But we want to show that the product of two Gaussian distribution is again a Gaussian distribution. Yeah. And maybe we remember this from our maths classes, but we don't remember exactly how the mean values add, how the variances add, and so on and so forth. Yeah. So we need to simplify that expression. Yeah, we want to simplify the expression of just a plain product of two Gaussian distributions. Yeah. And how do we do that? Very simple. We use simplify. Yeah. So if you don't know what to do, just use simplify. Yeah. Usually it's quite clever. Yeah. You just use simplify. Yeah. And if you look at it, what did simplify do? Do you recognize this here? Here. This is no longer the product of two Gaussian functions. Yeah. It's just one Gaussian function. Yeah. Yeah. It's just e to the sum of these two exponents. Yeah. Yeah. And sorry, what did I do it again? Okay. Okay, sorry, and it doesn't simplify. Sorry, I did it right. It doesn't simplify it further. Yeah. So, but that shows you how this can work. Yeah. So it's very easy to use. Yeah. So there are many other. I mentioned a few. Yeah. There are many other expressions to simplify expressions. Yeah. For instance, if you want to cancel a common factor in the numerator and denominator, yeah, you can use cancel. Yeah. Expand we saw, factor we saw. You can use a RADSIMP. Yeah, if you want to rationalize, make rational some expression. Yeah. Simplify we have, and then there is a special simplify for trigonometric functions, yeah, which is TrickSim. Yeah, very often simplify does it automatically. Yeah, but if maybe for whatever reason it doesn't work, you can force it with TrickSim. Yeah, and there are many more. Yeah, but with these, you should have a basic setup for working. Yeah. Okay. Let's give a look at another example. Yeah. Okay. So this is very simple. Yeah. What we have here. Sorry, let's do just. It's easier to. Okay. Sorry. Again, these expressions. What doesn't it work? Okay. sorry, what did I do? Okay. Ah, sorry, the result is already there. Sorry. I didn't see it. Yeah. So what we have here is sine squared plus cos squared. Yeah. And you all know the sum is 1. Yeah. But we just want to see if SymPy knows. Yeah. And SymPy, of course, knows. Yeah. Sorry, it was so small I didn't see it. Yeah. It's just 1. Yeah. So all trigonometric expressions are here. Yeah. We can try even more complicated one. For instance, everybody knows that sine square plus cos square is 1. Yeah, but how does it work for the hyperbolic functions? Yeah, is sine hyperbolic square plus cos hyperbolic square 1 or not? Yeah, and of course it's not. Yeah, so that if you have forgotten, yeah, you can maybe try. Okay, maybe there was a minus somewhere. Yeah. And if you do with the minus, it's 1. Yeah. So the beauty of SymPy is you can really use it as a formula collector. Yeah. If you forget something, just type it in and bang, it comes out. That's probably much faster than to Google it. Yeah. You once you have a basic feel for it. Yeah. So and of course you can use it also the other way around. Yeah, for instance, you have in this case you have the sine of x plus y. Yeah, but you want it expressed with sine and cosine. Yeah, and then what do? You use expand. Yeah, and it gives you the addition theorem for the sine and cosine. Yeah, so that's really. And we could practice every formula in every trigonometry book, yeah, and it will work. Yeah, but it just this is more about showing you what is easy to be done. Yeah, and then when you need it, you use it. Yeah. So you can not only manipulate equations, yeah, you can also solve equations. Yeah, and I will give you here just one example because I know that later in the week you will have differential equations, partial differential equations, and maybe the people there will also, the lecturers there will also address how to do it in SymPy. Yeah, but I think they will mainly focus on numerical. But anyway, let's assume you have a quadratic equation. Yeah, and maybe you probably all learned at school, but sometimes you forget what was the formula. Yeah. And you want to solve it for x. Yeah, so nothing more simple than that. Again, sorry, I don't remember where I added here y because we don't need it. But anyway, yeah. Sorry, forget about the y. We just don't need it. Yeah. So what you see the setup of SP solve. Yeah. You need the equation here, and SymPy assumes that this expression is equal to 0. Yeah. So if there is some +3 somewhere, just put it equal 3, you put it on the other side so that it's equal, the expression is equal to 0. Yeah. And then you solve it. Yeah. SP solve and it gives you 1. Yeah. So there is one solution and that is 1. Yeah. In this specific case. Yeah. So that's really very nice. Yeah. You change the -2x in plus, and all of a sudden it's -1. Yeah. You can also have equations where there's more than one solution. Yeah, and then in angular brackets it gives you there is solution -1 and there is solution 1. Yeah. So it's and for many simple equations, also differential equation, you can use the same strategy and it works. Yeah. So it's really very practical. Yeah. For instance, now I remember why I needed y. Yeah. So maybe you want to solve this expression. Yeah. X over y minus x plus x minus y over y equals 0, and you want to know what is x. Yeah. As a function of y. Yeah. So now remember why we needed the symbol y. It was for this example. Yeah. Yeah. So SP solve and bang. Yeah. And you're welcome to be creative and try SP solve for whatever comes up to your mind now. Yeah. And it should come up with some result. Yeah. So SP solve is also something very useful. Yeah. Sorry, there's a question in the chat whether SymPy can use the steps. Then you need to force him to do it step by step. Yeah, you can ask him to do it step by step. Yeah. I don't think there is a function like in Mathematica where it shows you the step that it does. But to be honest, I'm not sure. Yeah. But very good question, Vincent. Thank you. Yeah, you can here another example of a more complicated equation, x plus y minus 2, x minus y plus 1, of a system of equations. So we have a system of two linear equations, yeah, and you want to solve it for x and y, yeah. And of course, the output gives you x is 1/2 and y is 3/2, yeah. And again, you see, it gives you the rational expression and not the float number approximation, yeah. So that's really very nice. So SPSolve is very useful for polynomial equations, for systems of linear equations, and so on and so forth. Yeah, you can, and then the sky is the limit. Yeah. Okay. Now let's go back to school. Yeah. You know, if you looked at the SymPy documentation, you saw that there are packages for everything from physics, chemistry, quantum mechanics, blah, blah, blah. Yeah. But let's stick to the basics. And, you know, if you need a more advanced application, just browse the examples in the documentation for the class of problems that you're interested in, and you will find. Yeah. So, but calculus is also very useful. Yeah. Let's start, you know, just, you know, you probably know it. It's just only a matter of showing what you can do. Yeah. You can do sums and products. Yeah. And surprise, surprise, the commands are summation and product. Yeah. So as you see, it's not very difficult to remember these commands. Yeah. Let's assume you want to evaluate the simple sum of k equal 1 to n up to k. Yeah. Sorry, from k equal 1, the sum of k from k equal 1 to n. So 1 plus 2 plus 3 plus 4 plus 5 plus 6. Yeah. And you know, you probably remember there was a formula for it, but maybe we have forgotten. Yeah. So very simple. Yeah. So now we need two symbols. Yeah. We need the symbol k and the symbol n. Yeah. And now we need the summation of k. Yeah. Over k from 1 to n. Yeah. And then bang. Yeah. It comes with a solution that young Gauss discovered when he was a child. Yeah. Yeah. So it's very, and if you want, we could factor it and simplify it and blah, blah, blah. Yeah. But this is what comes by default. Yeah? So it's very important, you know, the symbols. Yeah. SymPy is quite clever. Yeah. It remembers, it understands when you want the integer symbol or a real symbol or whatever. Yeah, you can force it also to use symbols to be integers or not. And I think we have later an example where that is the case. Yeah. Okay, so sums are easy. Yeah, and you can try whatever sum you want. Yeah. Let's do a somewhat more challenging sum. Yeah. Let's do the sum of 1 over 2 to the power of k, yeah, for k equals 0 to infinity. Yeah, this is a little bit more challenging. Yeah, maybe we don't remember it from school. Yeah, same strategy. Yeah, symbol k. Yeah, because infinity is a constant in SymPy. Yeah, remember it was the double O. Yeah, so SPOO stands for infinity. Yeah. So again, what do we do? SP dot summation 1 over 2 to the power of k, and then we sum k from 0 to infinity. Yeah, and the result is 2. Yeah. So very simple to do. Yeah. Okay, and I think sorry, am I now at the end of what I wanted to say? Yeah. Sorry, I think we went way faster than I thought we would. Yeah, but maybe let me show you something else. Yeah. You know, you were wondering about, someone was wondering about the Greek symbols. Where do I have them? Sorry. Here. You see, can you see this line? Yeah. The symbols can be Greek letters. Yeah. When I mentioned what this Jupyter Notebook allows you to do, yeah, is it allows you to use a markdown language to write the comments. Yeah. And the markdown language is very similar to LaTeX. Yeah. So for instance, alpha is \alpha. Yeah. And and if you run it, it gives you alpha, beta, gamma, like you had there. Yeah. Sorry, you know, I've never done this before. That's why probably my time management was not particularly good, because now we have still lots of time. Is there any question that you have? Yeah, and then maybe we review it a little bit and see what else we can do. Any question? Or did I go too fast? I don't know. Sorry, I thought I had 40 slides. That could be enough for an hour, some bit, but we went too fast. Yeah. Then maybe let's do, you know, sometimes it's good to sorry, we need to start from the beginning. Let's review maybe a little bit what we have done, if you don't have any questions. Yeah. Okay. And Kumalo says we went too fast. Okay. Sorry. Then let's review briefly what we have done. Yeah. Sorry. Why doesn't it work? Sorry, something went wrong here. Let's try again. Sorry. Okay. Somebody complained that we went too fast. Yeah. Okay, then let's maybe review briefly what we did. Yeah, just the highlights, the thing to remember. Yeah. So the first thing was sorry, now I'm going, sorry, I want to go slow and I'm going fast. Yeah. Okay. Someone mentioned what library do we need? Yeah. Essentially, we need only SymPy. Yeah. I imported here NumPy because at the beginning I wanted to show you the difference between SymPy and NumPy in dealing with numbers. Yeah. And I imported matplotlib, but I didn't. Oh, sorry, but I didn't plot anything. Yeah. The reason for that was that you've just learned matplotlib. Yeah, if I remember correctly. Yeah. But SymPy uses also almost matplotlib, but the syntax is a touch different. Yeah, and that's why I thought, if you need to plot, just use matplotlib and don't do it from SymPy. Yeah, you can do it as well. Yeah, but the syntax is a little bit different. I thought maybe it's important not to confuse you too much at the beginning of your Python career. Yeah. So this is essentially what we need to do SymPy. Yeah, you import SymPy, and I said I import it as SP. Yeah, if you Google around, and some people import it as SYM, some people import it as SY. Yeah, you can import it as whatever you want as long as it's consistent. Yeah, I like SP because it's a little like NP for NumPy. Yeah, but that's personal preference. Yeah? What we need, what makes it easier is this init_printing, because this is the command that makes all equations look fancy. Yeah, like printed. Yeah, if you don't do that, they look a little bit ASCII code wise. Yeah, which might also be okay, but it's not particularly pretty, and since it's 2023, people would like to have a how it goes. Yeah. Okay. So here was the basic difference. Yeah, square root of 3 in normal Python is 1.7 blah blah blah, and if you do it in SymPy, it's just a nice square root of 3. Yeah. Sorry, in Jupyter you just press Shift Enter. Yeah, so you just do. Sorry, where is my cursor? You just do Shift Enter. Yeah, Shift Enter. Yeah, sorry, I just see the question. Yeah. So this is very nice. Yeah. How did I write the symbol mu in line 29? We get there. I don't remember. Yeah. Anyway, the same. Once you have, if you want to be consistent with rational numbers, you can force it to use rational numbers. One typical command is simplify, but you can also use the command rational. Yeah. If you do SP rational, for instance, 1,7, it gives you 1/7. If you do rational 2,3, it gives you 2/3. If you do 4/5, it gives you 4/5, and so on and so forth. Yeah, that's that's okay. Yeah, so that's really very nice. Yeah. Another very important thing, you know, the repetition now. Yeah, all the standard constants are there. If you want pi, just sp.pi. Yeah. If you want e, is this sp dot, and it's capital E, not and I wonder why. I don't know, but what is funny is that there's also infinity. Yeah, SP00 stands for infinity. Yeah, so in particular, if you do sums, integrals, is a very useful thing to have. Yeah, you know, numerically you don't have infinity. You need to put a very large number. Yeah, but if you do it symbolically, it's easy. And you can do complex stuff as well. Yeah, so the imaginary unit is sp.I. Yeah, capital I. Yeah. Okay. And then we mentioned, you know, sometimes maybe at the end of a calculation, you want a real number, yeah? And for that, there is the function eval_f, yeah? Evaluation of the function, yeah? And that gives you the real number, yeah? And we, you know, we played around. If you want it per 100 digits, you just type in the 100 and then a very long number for the square root of 2. Yeah, so that that's okay. Yeah. Okay. So, and then we had the little example of calculating the 100 digits of pi, and that's of course the same command as before. Just attaching the eval function after the pi. Yeah. So sp pi. Sorry, here in the example I wrote 100, but then we played with 200, and you see it's very easy. Yeah. So, as I mentioned, the crucial thing in SymPy is to introduce symbols, yeah, and to introduce symbols, it's very simple, yeah. For instance, if you want to manipulate expression with x and y, you use sp.symbols, and in inverted commas you define x and y, yeah. So that's very straightforward, yeah. Once you have that, you can sorry, this maybe we skipped that because it was just a comment, and here we come with the Greek letters, yeah. You see, you can SymPy understands Greek letters, yeah, SP symbols, alpha, beta, gamma, yeah, and then if you look what is alpha, it tells you that's alpha, yeah. and you can super and subscripts. Yeah, this is the subscripts are underscore. Yeah, and superscripts are the head. Again, this is exactly like in LaTeX. Yeah, which is a text processing open source package as well. Yeah, the same notation as there. Yeah? and if you do that, if you print then this delta 1 2, it gives you delta with underscore 1 and underscore 2. Yeah. Now expressions. Yeah. Once we have the symbols, we want to start put them together in mathematical expression. Yeah, and that is really straightforward. For instance, if you have 2 times x plus y, yeah, 2 times y, you do 2 times x times y after you have defined x and y as symbols. Yeah, so that's really very simple. Yeah. And once you have the expression, you can manipulate them like you would with pen and paper. Yeah, you divide by 2 and so on and so forth. Yeah. And then we had a little bit more complicated example. Yeah, did I print it out? Yeah, the expression 2 was e to the power of x times sinus x plus e to the power of x times cos x, and that was very simple. S x times s sine plus s x times s cos. Yeah. And we learned how to simplify expressions. Yeah. One command was factor. Yeah. Which factors out, in this case, the exponential. Yeah. It was also easy to expand it back. Yeah. With expand. And if you're not happy with that, you can simplify it further. Yeah. With simplify. Yeah. So that we learn factor, expand, and simplify. Yeah. You can use them to simplify. Good morning. To simplify expressions. Yeah. So that's very, very nice. Yeah. I didn't have an example for collect, but that allows you to collect a term and push and force it, let's say, out of to collect terms. Let's say you have a polynomial with various factors, x to the power of 3. Yeah, and you want them all outside. So you can collect all the terms with x to the power of 3, for example. Yeah. There is a question about the limitation of the degree of the polynomial. I think formally not, but it might take time. If SymPy is not the fastest. Yeah. If you go, sorry, I think I have the link somewhere here to the SymPy documentation. You find the list of all mathematical functions, and that's fairly natural how they are called. Yeah, so that's very easy. And then we had maybe a slightly less trivial example, and this is where the question comes. Yeah. And I haven't answered it because, to be honest, I don't remember. You see here, I made a mistake because I imported again the symbols. Yeah, but they should be. I don't know. It works like this, but I don't know if it works. I don't know what I did here. To be honest, I don't remember. What did I do? Let's try. Sorry, let's try. Sorry, we are here. Let's add a cell and try z equal symbols. Let's say, what do we have? Theta. And then we want z. Okay, now it doesn't work. To be honest, I don't know. What did I do? I know those are the mysteries of programming. Okay, I will find out, I hope, for this afternoon. Yeah, I tell you again. Anyway, I don't know, something magic happened here. Anyway, I don't know, we will find out. Yeah. Sorry? No. They, you see, they're asking why in the symbol, it already uses the Greek symbol.
Oh, that is strange.
Yeah, no,
The pretty printer, it's when you use the printer to.
I know, but that we use. But in the other cases, that only in that line it does. I don't know. Something must have went wrong. Sorry.
What happens if you use double quotes instead of single quotes?
Ah, that's an interesting one. No, in the others we always had the double quotes. You know,
Doesn't make any difference. Okay.
Okay, I don't know. I will find out. Sorry, but anyway, I don't know. There are always mysteries. Okay. Then, and as an example of something a little bit less trivial, we generated two Gaussian distributions, yeah, and we multiplied them and simplified them to show that the product is again a Gaussian distribution. Yeah, so that was as complicated as we got. Yeah, and with simplify. Okay, so I did that line. Ignore. Yeah. Again, I summarize here again a little bit the function that we can use to simplify. Some we had, some that we didn't use is cancel. Yeah, if you have a common factor in numerator and denominator, you can force it to cancel it. And then one that is very, very useful is trig simp. Yeah, when you have trigonometric expressions and you want to simplify them. Yeah. One thing that maybe you might want to see. Yeah, if how do you do tables in slight deviation in Markdown language? Yeah, it's very simple. Yeah, you see, you start the table, the column with the how do you call that symbol, with the vertical line, yeah, and you finish it with that, and you separate the column with that. If you want a line to underline the title row, and then you can generate automatically a very simple table, yeah. And this is a typical example of things that you can do with a Markdown language, yeah. Okay, but that's maybe a topic for another talk, yeah. So we practice a little bit the trigonometric functions and the simplification with trig simp, yeah. And you know, I hope I convince you that SymPy knows all the addition theorem for trigonometric functions and things like that, yeah, which was very good. Yeah. Then I showed you, I think, two examples of solving simple polynomial equations like quadratic equations with SymPy, yeah, and the magic command was solve, yeah, SP solve, yeah. And the trick is that you need to the equation, write it in a form that you have the expression equals 0 on the right hand side, yeah. And in SP solve, you add the expression on the left and indicate for which variable you want to solve it on the right after the comma, yeah. So in this case, is it SP solve x squared minus 2x plus 1 comma x, yeah, and bang, the result is there, yeah. And we tried a few versions. Then we tried also a system of a more complicated expression where we want that depends on x and y, and we want to know what is Rx expressed in terms of y, yeah, that works as well. And then we tried a linear system of equations, yeah, x plus y minus 2 equals 0, and x minus y plus 1 equals 0, and we solve for x and y, and SymPy gives you x equal that and y equal that, yeah. So that was very useful. Yeah, and then we started a little bit of calculus, yeah. We practice sums and products, yeah. And the commands are summation and product. And for instance, typical example was the sum k equal 1 to n of k. and you just write it as the summation of k, yeah, for k from 1 to n, and bang, you get the result. Yeah, that's very easy. Yeah. And as another example, we use 1/2 k. And in this case, okay, you have just a simple k. And the nice thing of this example is that you explicitly see that you can sum to infinity. Yeah. So the SymPy knows that. Yeah. Yeah. Okay, now we went through twice. I don't think we, I don't think we will have quizzes. We'll have just after the break a tutorial where we compiled a few simple things that you can try to solve. But the basic idea now with SymPy is think of what you might need in your life and try to solve it. Yeah. Or if you are not that creative, Google some expression that you don't remember and see if SymPy can give it to you. Yeah, it will be fairly straightforward. Yeah. Yeah, someone asked in the Slack channel about the imaginary I, and that is SPy capital I. Yeah, yeah. So that should be all right. Yeah. Yeah, no, those are the typical mistakes that people do. Then let me give you maybe a preview of what we will do this afternoon. Is it here? No, this is the tutorial. Yeah, this afternoon we will keep doing a little bit of calculus. Yeah, we will differentiate and integrate. Yeah, and then we will do and then we do a little bit of linear algebra. Yeah, which might be very useful. Yeah, so you see, we will do Taylor series, a little bit of vectors and matrices, scalar product, cross products, manipulation of matrices, and at the end, yeah, we do a nice error. Yeah. Okay, I don't know what it was, but I will find out. Okay. Is it no? So, oh, sorry, what did I do? Okay, I will sort it out. Okay, we know some nice error at the end. Yeah, yeah. So that's what we will do in the afternoon. Yeah, we'll do a little bit more advanced applications, so that you see that you can easily cover all linear algebra and calculus curriculum. Yeah, so if you forgot something, it's very easy to reconstruct with SymPy. Yeah. Someone asked, how can you stop everything? Usually you press stop in the Jupyter notebook and it should stop. Interrupting camera still. No, it's not supposed to take a long time. There must.
Are you going to stop sharing?
Should I? No, I don't know. This gentleman asked how can stop the Jupyter notebook from running. Yeah, but
you can close the server.
Sorry.
You can stop the server.
Yes.
Or you can just disconnect from it, and the server goes on running.
Yeah. You just press the kernel, or you just close it and open it again. Yeah, yeah. So that should be all right. Yeah. Are there any more questions from the guys here in the audience and online? So it went a little bit too fast, probably, but I've done this for the first time, so it was difficult to gauge a priori the time that we would need. But at least we went through it, and we had a revision session all in one. Yeah, and I guess with the tutorial afterwards, something will stick. Yeah.
I think a lot of people probably started very quick, and a lot of people, we had some people arriving late even. So they were still trying to figure out how to start.
Okay, but if we finish now, you still have 20 minutes before the coffee break to play around, and that's the only way to learn it. Yeah, you don't learn it by someone telling what to do. You learn it by doing all the mistakes and try to fix them. Yeah, that's the only way of learning it. Okay, then I would suggest that we stop here for now. Maybe you have another 15 minutes, maybe to play around before the. I think the coffee break is 10:30. Yeah, before the coffee
Prof?
break. Yeah, and yeah, Benjamin.
Prof, could you do an overview of Jupyter Notebook just for some students that aren't familiar with it?
Sorry, Benjamin.
Can you do an overview of Jupyter Notebook?
Ah, okay. Yeah, we can do that. Then let's go. So if you all have Anaconda, yeah, the green little circle. Yeah, you create Anaconda, and you probably you use mostly Spider. Yeah. Jupyter Notebook is this one here. Can you see it here? The one thread.
Just
yeah?
share screen, Prof. Just share screen.
Ah, sorry. Sorry, I just thought. Sorry. Thank you, Benjamin. Okay, let's open. Let's share again. Okay. No, sorry. I need to. Sorry. I need to share Jupyter. Where is it? Let me do it. I just shared the desktop. Sorry, it's easier. Yeah. Can you see it now?
Yes.
Yeah, sorry. Okay, so here is Jupyter Notebook. Yeah, you mainly work in Spider, which is probably the most professional tool to code in Python. Yeah, the reason why I chose Jupyter Notebook is because it has the presentation feature that is really very nice, I think. Yeah, and then you press launch. Yeah. And then it drives you back to opens your browser. Yeah, in my case it's Safari, and then you can you go to your document. Let me go to where I have the lectures now. Yeah, I go here, and here you see I have SymPy, and somewhere here I have notebooks. Yeah, and today we were in SymPy lecture 1. Yeah, you click there, and it opens Jupyter Notebook in your browser. Yeah, if you don't have one file to open, you can create one. Yeah, you can just create one and save it wherever you want. Yeah, so that's the how to deal with Jupyter Notebook. Yeah, you see, you notice here there are 2 types of cells. Yeah. Here, this is a cell. If you go here, you see this is a. If you go to the cell type, you see there are different cell types. Yeah, there is code cell types and markdown cell types. Yeah, this is a markdown cell type. Yeah, so if I were to change it, the cell type, yeah, to code, yeah, and I run it, it wouldn't do much. Yeah, it just regards it as a comment. Yeah. But if I change it to Markdown, yeah, it uses all the Markdown command. And if you look at here, you see I have here started the line with a hashtag. Yeah, the hashtag means that's as a high-level title. Yeah. So look again. So this gives you this size. If I add, for instance, 2 hashtags. Yeah, it makes it a little bit smaller. Yeah, if I add 3 hashtags, it makes it even a little bit smaller. Yeah, so you have a kind of way of choosing the level of headline in your Markdown editor. Yeah. So let's give a look at the code of this. Yeah, you see this is now also a Markdown cell. Yeah, and I just wrote here SymPy is an open source computer system, and the link to the website, and then shift return, and it looks like a nice edited text. Yeah.
Wikis normally will put in Markdown.
Sorry.
Most wikis based on Markdown.
Yes. It's a very simple Markdown language. Yeah. And let's and you see this cell here is a code cell. Yeah, because this I can run. Yeah, and you see something happened here. Yeah. Another thing that is interesting, if you look here, if you click here on view, yeah, and cell toolbar, yeah, you can choose a slideshow, yeah, which is what I did here. And then you have the possibility of making a slide, making an input line of Python, a slide. Yeah. So if I press then here on the slide thing, yeah, you see it makes the title of a slide. And at the bottom here, I have two arrows. This to move within the same slide, and the arrow to the right to move to the next slide and back. Yeah. And you see, this is a slide, this is a sub slide. Yeah. So that's how it looks like. So you have the slide. Yeah, and the sub slide is part of the same slide, but appears on another page. Yeah. And if I press here the link to the right, a new slide starts. Yeah. And you can see it here that we will proceed is a new slide with three sub slides, or before sub slides. Yeah. So this means that each of these blocks opens up on a new page. Yeah. Yeah. If I do on the contrary, sorry, where is it? I have some of the fragments. Let me do it. I can show you here. Yeah. If you let's assume I do this a fragment. Sorry, I don't want to skip it. I want it as a fragment. Yeah. What will be the difference? Or let's do both as fragments. Yeah. So you see, I do the two sub slides. I have a slide, a sub slide, and two fragments. Yeah. What will happen? So let's see. I have the title. Yeah. Then I have the sub slide. It opens it in a new slide so that you can say it in big. And then come the sub slide, the fragments. Yeah. The fragment is projected in the same screen, and the second fragment as well. Yeah. And now comes the next sub slide. Yeah. On the next page. Yeah. So you have the possibility of choosing how you want to present it. Yeah? And in order to have this installed inside Jupyter Notebook, you need to install in Anaconda a package called RISE. Yeah, R-I-S-E. Yeah, that allows you to have this functionality that you just press here and it projects it like it creates a slide presentation if you want. Yeah. And that's essentially all you need to know for Jupyter Notebooks. Yeah, you know, to run it, it's shift return. Yeah, and I think that's it. Yeah, and you know, and for symbolic calculations, I think it's a nice, useful tool because you want to go back and see how it looked like, and see it step by step. In a nice LaTeX kind of setup. Yeah. The other thing that is really nice, I like very much, and I think it's the easiest way to create tables. Yeah, is this markdown way of creating tables. Yeah, which comes, I think, for those of you that use Emacs, it's the markdown for tables from org mode. Yeah. So it's very simple, yeah. So and it creates, you see, even if in Markdown it looks ugly, yeah. You know that the columns are not the same, but just a little press Shift and Enter, and it aligns it absolutely beautifully, yeah. And what you can also do, for instance, if you add here a dot, yeah, what will it do? No, sorry, this I always forget how to do that. Now there is a way of aligning it to the left. Yes, you see now it's aligned to the left. Yeah. So with the dots at the beginning or the end, you can choose whether to align it at centrally to the left or to the right. Yeah. And I think we've done it. We had another few tables. Where was it? This table is also. Yeah, you see here it is. Yeah, with the two dots, you can align this column to the left and this column to the left as well. Yeah, so like you can see here, they're nicely aligned to the left. Yeah, and if we would have put the dots on the other side, yeah, we would have aligned the table to the right. Yeah, so now all expressions are aligned to the right. Yeah, but I think for our purposes, it is nicer to have them aligned to the left. Yeah, like that. Yeah, and I think so. I don't remember now if you do it with both dots, it does it centrally. Yeah, you see now it's centered. Yeah, so you know this is a matter of personal taste. Yeah, but I think left centered is nice. Yeah, so that is very nice. Yeah. The other thing maybe. Yeah, no, that's okay. Yeah, yeah, and you see, and it does the description of the column. It does it in boldface automatically. Yeah. Yeah, if you want them in italics, I think it's underscore. Let me try. Sorry, I don't know. Yeah, you see, underscore makes it bold by default, and underscore makes it italics. Yeah. So these are simple ways of editing nicely in a Jupyter notebook. Yeah, you see here again the title, we had the one hashtag. Yeah, these I can show you. Yeah, how do we manage to make in the markdown language the equation look nice? Yeah. Yeah, we use essentially LaTeX. Yeah, so the mathematical environment for an equation starts with $2, yeah, and ends with $. Yeah, and in the middle I write the equation x squared minus 2x plus 1. Yeah, and if I want the mathematical symbol in line, it's just $1. Yeah, the $double makes a new line. Yeah, and the single dollar makes the mathematical symbol in line. Yeah. So that's and I think that's all there is to know to if you want to add comments in this Jupyter notebooks. Yeah, I think that's okay. There was a question again about the built-in function to imports here. Here they are. Yeah. But essentially, you just need SymPy. I imported here NumPy as well because I did a little demonstration of the difference of numbers in SymPy and default Python. Yeah, but it would work without those as well. Yeah, and forget about the warnings. That was my problem. I had some issue with some fonts. I don't remember that I didn't know how to solve, and that's why I killed the warnings so that it doesn't bother you today. Yeah. To get the projection tools, it's something called RISE. Yeah, R-I-S-E. Yeah, and you go. Sorry, I'm using Kim's Slack. Yeah, it's RISE. You go in Anaconda and you import the packages and you look for RISE. Yeah, and that is that makes the slideshow. Yeah. It's and you can do it also in Jupyter Lab, but I think in Jupyter Lab you need to import Jupyter Lab underscore RISE or something like that. Yeah, so that's very straightforward. Okay, any other questions? Okay, I explained how the slide window for equation works. I told you about RISE. Yeah, then I think it's probably now the good time to stop and